pretty quick. We've really talked about a lot of this stuff already, but we're going to talk about vertex forms of absolute value functions and quadratic functions. So we're going to focus on just, we kind of alluded to all this stuff last time, but we're going to look at, remember at the end of the last lecture, we were talking about how you can graph the functions. Instead of thinking of it in terms of translations, you can think about it as the coordinates of a vertex, and then you just build the function from the vertex, right? So that's how we're kind of thinking about absolute value functions and quadratic functions, and later we'll apply this to other functions as well. Okay, so if we look at an absolute value function, this is our vertex form, right? And we call it vertex form because it shows us the coordinates of the vertex. The vertex is obviously at h and k, right? H is the x coordinate, k is the y coordinate. Now, for an absolute value function, think what a does. A is telling us how much we're stretching or compressing the function, but when we graph the parent graph for an absolute value function, the slope of the right leg we always said is 1, correct? And the slope of the other, the left leg, is -1. So the amount that we stretch or compress that actually ends up being the slope, doesn't it? So it works out pretty conveniently, but don't get too hung up on that. It's a shortcut, but think of why it becomes the slope of the right side and then -a becomes the slope of the left side. That's only because that's how much we're shrinking or compressing the function compared to its vertex, right? So think about multiplying the heights. That's really how we must do it, because the slope thing only works for absolute value functions. It doesn't work for any of the other functions. Okay, so what about this one? Let's just go through some quick examples of this. And honestly, I kind of just want to get you going, give you a chance to get through this as quick as we can so you can just get working on this and get some practice. What about this one right here? What are the coordinates of the vertex on that one? Jace.
One comma 4, or 1, yeah, 1, -4.
-4, okay. Anybody want to slightly tweak that? Very close.
Wouldn't it be -1?
-1, good. And remember, because h is the value that we're subtracting from x. So x minus what would be x plus 1? X minus a negative becomes a positive, right? Does that make sense? Okay. What about the axis of symmetry? If I graph an absolute value function, think what that looks like, right? If I graph an absolute value function, so say I've got an absolute value function like this one right here, where the vertex is at -1, -4. So here's one that has a vertex at -1, -4, and a is equal to 1, so it's just a regular slope of 1. What's the axis of symmetry of that? What do we mean by an axis of symmetry on this one? What do you think, Duluth? What do we mean by an axis of symmetry?
Is it the vertex? Because like if you fold the doesn't make any sense. Sorry. I was just thinking it was like the vertex and like the x coordinate.
Okay, so you're pretty much right on that. It has to do with the vertex, but when we talk about an axis is always a line, right? So it's the axis of symmetry is a line, but and I'm just, I'm throwing this out there. I haven't told you this stuff yet, but I'm just curious if you guys can come up with this on your own. What do you think the axis of symmetry would look like here? I'll throw it out to the whole group.
It would just be like a line down the middle.
Okay, good. Yeah, it's a line, and it's a special line because it's the line of symmetry, right? The axis of symmetry is the line that we could fold this thing over so that it would overlap on itself perfectly, right? So here's our, come on. Here's our axis of symmetry. It's just this line, whoops, that line right there. I could fold it over that line and it would fold perfectly, right? It's got that folding or reflective symmetry about that line. Well, if the coordinates of the vertex are at -1, -4, what's the equation of our axis of symmetry? If it's a vertical line, how do we name a vertical line? What do you think? Somebody just chime in here and tell me what would the equation of that axis be? Anybody?
Maria said x equals -1.
Oh, yep, I see it up there. Good. Yep. X equals -1. Exactly. And that's how we name a a vertical line, isn't it? We name a vertical line by its x coordinates everywhere, right? So whatever the x coordinate of the vertex is, it's a vertical line through that point. And so we could say in general then that the axis of symmetry is always going to just end up being x equals h. Now, where did that? I'm going to add that up here. Somehow I don't have a blank for that anymore. Yeah, I don't know where that went. So the axis of symmetry, let's add this to our notes. Is always going to be x equals h. Every time, right? I don't know where that went on my notes. Okay, so let's get... If we're going to graph this one, and these, we'll go quickly on these. We just want to be able to identify where the vertex is, and then we'll build the function based on our vertical dilation factor, which is just a, right? Remember from our discussion about transformations, that's all a is the vertical dilation factor. It happens to be the slope for absolute value functions, but I'd almost prefer that you forgot about that part. Just think about it as a vertical dilation factor. So where does the vertex sit on this one, Dawson? What are H and K? Oh, there you are, Dawson. Now I hear you.
All right, so k would be 4, and then x would, or not x, h would be 0.
There you go. Good, perfect. Because nothing is being subtracted from x, so x is 0 and k is 4. So our vertex goes right there, doesn't it? The point 0, 4. Now, what about, how am I going to draw the shape of this thing, right? We want to think about dilating a regular height on this. Normally, we would go over 1 and up 1, correct, on an absolute value function. Our parent graph, remember, just looks like this, right? Our parent graph, we have a slope of 1 there, slope of -1 there. So I'm over 1, I'm up 1. If my value of A, my dilation factor, is -7, how would I get to my next point? Instead of going over 1 and up 1, what would I do, Chloe?
You would go down 7 another one.
So I'm going to go, okay, right. But so I see what you're saying. But instead of going over to the right by 1, in my normal height, if I go over by 1, my normal height of the function would be 1, right? That distance right there.
Yeah.
So we're always going to multiply that by the dilation factor of, in this case, -7. So 1 times -7 equals -7. So that's telling me When I go over 1, I'm going to go up 1 times -7, which is down 7. Does that make sense what I'm doing there? So there's my -7. There's my next point. You guys see give me a 1 to 5 on that. Does that make sense when I talk about that stuff? Because I can't really see your faces here, so I can't always judge. Okay. That's what that dilation factor does. It takes the height of the parent graph. When I say height of the parent graph, I mean how far is a point vertically above the vertex, and it multiplies the parent height by the dilation factor to get the dilated height. So we could have gone over 2 and up 2 and multiplied that by -7 to go down 14, but that's just not as convenient, right? We're just going to go over 1 and down 7. So then we know that our graph looks like, oh, that was pretty good. Looks like that. And then I can use the symmetry of the shape to reflect it over my axis of symmetry right there to get the other point. There's the whoops, sorry, that's not it. There's my reflected point right there. And I can graph that side. So it's a real skinny V shape that opens down. Okay, give me 1 to 5, everybody. Quick. Okay, type it in chat if you're not putting your cameras on. I just want to make sure everybody's with me on this. I got to know how we're doing. Okay, good. Thank you. All right, let's try one more. How about this one? So let's see. Andrew Saxton, what are the values of H and K for this one? H and K and A. Tell me all 3 of them.
A is -6.
Okay.
H is -1. And K is -2.
There you go. Good. So -1, -2. So -1, -2 puts us there. And then if A is -6, instead of going over 1 and up 1, I'm going to go over 1 and do what with it, Mr. Demanu?
Over 1 and down 6.
Over 1 and down 6. Good. So over 1, down 6 puts us right there. We could reflect that over our axis of symmetry to get another point over there. And there's our shape. Now you can see why when we're doing absolute value functions, it makes it really easy because the -6 also just becomes the slope, right? The slope of the right side, okay? Okay, so let's work backwards now on one of these. Everybody take a look at this one. Just try this on your scratch paper here. Just be kind of working away at this one. There's the picture. I want you to come up with the function that matches the graph. So we're by inspecting the graph, we would have to extract the values for A, H, and K to plug those in, right? Okay, Alan, what are the values of H and K?
Did you say me?
I said Alan.
Oh.
Yeah. Oh, okay. No, it's on. You got it, Adelaide.
So H is 4.
Careful.
No, -4.
There you go. -4. K is?
And K is 3.
There you go. Good. And we see that because those are just the coordinates of the vertex. Okay, now we got to be, it's a little bit tougher to find A on this one, right? We've got to ask our, what do you think? Can you give me an answer on that one, Adelaide, what A is? I guess it's not that bad for an absolute value function. It's a little bit, when we get to the parabolas, it gets a little trickier. Okay, Rebecca's asking, is it 1/2? You're correct, it's 1/2. How'd you get that, Rebecca?
I know if you multiply 1 times 1/2, it would give you the slope of.
Okay, good. So that's a good way to look at it. So she's saying normally we would have gone over 1 and up 1. We would have ended up there, right? Well, we must have multiplied our height by 1/2. It might be easier to use this point right here because it's convenient. Look, this one, we can see that when we go over 2 from our vertex, we're going up by 1. Normally, we would go over 2 and up 2. And so we could make that comparison and say, okay, we must have multiplied 2 by 1/2. But either way works, right? And then, of course, you can sort of cheat a little bit with an absolute value function and just say, okay, well, the slope of that right leg is 1/2, so I know A is 1/2. Okay. Either way, we get, when we plug that stuff in, what do we get for our function then? F of x equals, well, there's my 1/2. I've got the absolute value. Now, what does the x minus h become inside? What should I get there on that one, Abby?
X plus 4.
There you go, good. X plus 4, and then finally I'm going to get, what, a plus 3? And so there's my answer. Okay. All right, so now let's, really that just sort of is a warm-up for us for parabolas, for quadratic functions. So just like before, we know that this is our standard form, right? Our vertex form, sorry. A times, but in this case we have f of x equals a times the quantity x minus h squared instead of the absolute value of x minus h. But we always know that h is the value that we're subtracting from the input x, right? And then we add k outside of the function. Once again, just like before, we know that hk is the vertex. We know that x equals h is still our axis of symmetry. And we know that A determines the width and the direction of the parabola. And let's remind ourselves real quick what we call that. Remember, A is the name of that is the vertical dilation factor. And think what that means, right? We remember doing dilations in geometry. Dilations are when we kind of scale up or scale something down, right? Well, in this case, we're only scaling it up or scaling it down vertically. So it's only a vertical dilation factor. We're not expanding the whole thing, just vertically. So we know that if A is greater than 0, the parabola opens up, of course. And if A is less than 0, so A is negative, the parabola opens down. And this is, this is vertex form because it shows the vertex on a quadratic equation with respect to its parent function. And what's the simplest quadratic function? What's our parent graph for this one?
Y equals x squared.
There you go, right. Or f of x equals x squared or y equals x squared, right? That's our parent graph. Okay, so what about this one down here then? The axis of symmetry for this one must be what? Rebecca Bertram, what's going to be, for the example at the bottom here, what's the axis of symmetry?
Would it be -7?
Yeah, x equals -7, right? Because we're talking about an axis, it has to be a linear equation. So x equals -7. Good. Okay, what about one like this? This is one, we're going to do an example. I want to do an example using the tools, but it might be a different equation, but it's the same questions. So given a quadratic function, you're going to be asked on this assignment, this is just like a sample problem off the assignment, to give the vertex, the axis, the domain, and the range. And then I'm going to ask you to determine the largest open interval where it's increasing or decreasing. It sounds like a lot of stuff, but it's actually pretty easy and goes pretty fast once you've done one of these. So I'll pull up this problem. Okay. I think this is the right one. Oh. No, what's going on? Oh, there it is. Okay. Okay, so one like this. First of all, what are the coordinates, Pagan, what are the coordinates of the vertex for this one? We'll just go through a sample problem here together.
Is it -3, -1?
There you go. So -3, -1. Very good. There we go. All right. Now we want to graph this one. Okay, so we know the vertex. That's helpful when we're graphing this. Oh, my. There we go. Now we can see it. So we know the vertex. So I'm going to use my parabola tool, and I'm going to go ahead and put a vertex at -3, -1. So right there. Now I need to know, though, how to graph the rest of the parabola. And that's where that value of a comes in. Would everybody agree a is -1/2? Everybody agree with that? Okay, so we're trying to, we want to multiply the regular height of a parabola by -1/2. So normally on a parabola, let's think about, let's before we do anything, how about if we, let's graph our parent function real quick first, right? For a normal parabola, it starts at the origin. We go over 1 and up 1, which means we would also go, can I zoom in on this? I don't think so. Which means I would go over 2 and up 4, which means I would go over 3 and up 9, right? Over 4 and up 16, over n and up n squared, whatever n is, right? So if I want to dilate this thing by -1/2, we want to pick the most convenient parent height to dilate by -1/2. Which height would that probably be of our regular points on our parent graph? Which height would be the height of which point would be convenient to multiply by -1/2? What do you think, Olivia? And what I mean by that is, like, if I went over 1, the height of the function is just 1. If I went over 2, the height of the function is 4 above the vertex, right? 1 wouldn't be so convenient because I'm multiplying 1 by -1/2 gives me a fraction, and those are harder to graph. So what do you think?
So probably the coordinates 2 and 4.
There you go. Good. So we'd go instead of going over 2 and up 4, we'd go over 2 and up 4 times -1/2, right? So we would go over, I'll draw another one here. So we would go over 2, and instead of going down 4, I'm going to go 4 times, instead of going up 4, I'm going to go up 4 times -1/2. Well, that's -2, right? So the shape of my parabola would be that yellow one right there, wouldn't it? Only I just need the vertex to be at -3, 1, right? So we're going to do the same kind of a thing, only we're going to do our parabola starting at -3, -1, and we're going to go over 2 and up -2. So it's hard to, boy, it's small, isn't it? I think that's right there. Okay, let's zoom in on that and make sure we got it. Well, it doesn't help much. I think we did. Okay, it's probably really hard for you guys to see, but we just, using the tool, we just went over 2 and up negative.
If you click the magnifying glass with the plus and it zooms in.
Can I make it even? Oh, there you go. Oh, good, thanks. So now I can make it even bigger. Okay, Good. So there you can see it better, right? We go over 2 and down 2. Okay? Check our answer. All right, look at that. So what's the axis of symmetry then of this one, Natalie? Questions for Natalie?
Would it be -3?
Yeah, so how do I write that as an equation then?
Oh, is it -3, -1?
Well, no, that's a vertex. The axis needs to be a line, right? It has to be that vertical line. So how do I say the vertical line through x equals negative? Well, I just gave it away, didn't I? It'd just be x equals -3. Does that make sense?
Yeah,
Oh.
okay, yeah.
Okay, good. Okay, good. Now it wants the domain. Okay, Maria, what's the domain of this function?
All real numbers.
All real numbers, good. And so how do they want us to do that here? I think they're going to want us to go ahead. I'm sorry. Oh, use interval notation. There we go. Whoops. Perfect. It's telling us. So how would you do that, Maria?
Parentheses, -infinity, comma, infinity.
There you go. Perfect. Okay. Good. All right. Now, what about the range? While you're at it, Maria, why don't you take the range?
The range is in below -1.
Right. Does it include -1?
Yeah.
It does, right? Okay, so it'd be,
So
go ahead.
bracket -1 and then comma infinity.
Okay, but we're going down, aren't we?
Oh, so it's -infinity, comma -1.
There you go. Okay, good. So why is it not? Oh, there we go. I had to click in there. Good. So yeah, so we're going to, it'd be y is less than or equal to -1. But remember, when we're doing interval notation, we have to put our left endpoint to the left of the comma and our right endpoint to the right of the comma, right? And how am I going to, you guys probably know how to do this better than I do. We'll try this. I've never done this in this program, but I'm assuming here I can put a -1, and then if I type, oh no, that's not working. So I think what I have to do here, I think that I have to just type this one in. I can't use that little template. I would just have to go parentheses, negative, infinity, comma, -1 bracket. Is that right? Is that how you do it?
Yeah, I usually just use the parentheses on the keyboard.
Oh, right. Okay, good. Yeah, that does make it quicker. Okay, good. So far, so good. Now, what about the last two? The largest open interval of the domain over which the function is increasing. Liliana, where is this function increasing? Where would an ant be walking uphill from left to right? To -3. Okay, good. So I go -infinity, comma, -3. What kind of symbol am I going to put after the -3, Liliana? Okay, so a bracket would mean I'm including the -3. Is the function increasing at -3? No, you're right, it's not, because that's a point of transition, isn't it? So what would I have to put there? Parentheses, good. Yeah. Does that make sense, everybody? That's a subtle point, but that's an important one. We can't include the maximum because that's not a place where it's increasing. It's no longer increasing there. It's transitioning from increasing to decreasing. Okay, and then by the same logic, I'll probably just do this one here. You can all see this. By the same logic, it's decreasing between 3 and infinity, right? So that would be one where I would put parentheses and a 3 because we don't include the 3, comma, infinity, parentheses. Oops, what did I do?
We put 3 instead of -3 for the last one.
Oh, yeah. I gotcha. Okay. So there we go. That's what I want. Okay. And now we're done. Okay, we good with that? Does that make sense? I'm going to ask you to do a bunch of those. Not a bunch, but several of those on the homework. Okay. How about, there's one more of those I want to do. I don't know why this one got skipped, but let's do this one. So let's try one more of these. So you can just walk me through this step by step. So Carrie, how am I going to graph this guy? Where's my vertex go? -6 and 2. Good. There's my vertex. And now what am I going to do here with my dilation factor? I'm dilating my normal parent heights by -4. So give me instructions to get my next point on the parabola. There you go. So, and let's switch that. We go over 1 and down 4. I mean, kind of nitpicky, but I think I did the wrong parabola. Whoops. I got to pick that parabola. There we go. So -6, 2, you said. And I go over 1 and down 4. Very good. Okay. What did I do? I must have done something goofy there. Let me try that again. I don't know why. I don't know why that's wrong. That looks pretty good to me. Okay, negatives. Try it again. -6, +2, over 1, down 2. So right there. Yeah, that's good. What in the world? Well, that's a little strange. How do I see, like if I just hit check, does it tell me what it's supposed to be? Oh, I see what I did. I didn't follow the instructions. Yeah, it says use the graphing tool to graph the function as a solid curve and the axis of symmetry as a dashed curve. Does that make sense? So I'm going to do another one. I was wondering what was going on. That just gives you more practice, Carrie. So where do I put my parabola this time?
-4 and 2.
-4 and 2. And give me instructions for my next point.
Over 1 and down 3.
There you go. Over 1, down 3. Okay. So there's that one. And then I want to do my axis of symmetry. Well, that's just going to be the line, vertical line through the vertex, right? And I want to make that one dashed. There we go. Now we got it. That's what they wanted. That's better. Okay. Then the axis of symmetry, we would just pick what it is. Well, it's x equals -4, right? Okay. Good with that? 1 to 5 real quick. Good. Okay. Good. All right. Moving on. So now I'm going to give you some information, and I want you to write the equation of the parabola from the information. So the vertex is at 1, 4, and we have another point on the parabola at 2, -1 on this one. So Kendall, what values am I tell me some numbers I'm plugging in up here on my parent graph, my vertex form.
A or no, H.
Okay, is what?
I'm not sure.
So it's giving you some information up here. So based on that information, what's H?
4.
4. Say it again. Not. Did you say 4 or 1? No, not 4. How about 1?
1.
Right. And how do we remember that? Because it's vertex form, because the vertex is given to us, H and K. Remember that here's how you can keep those straight. Alphabetically, H comes before K and X comes before Y. Okay, that's how you can always remember that. So the vertex is always going to be in the form. Whoops. God, this pen. H, K. So H is 1, K is 4, but we got to know A, right? So we're going to cheat a little bit and we're going to use a graph on this one. If the vertex is at 1, 4, and we have a second point that's at 2, -1, we can use that information to figure out what the vertical dilation is, right? If we think about a roadmap to get from the vertex to this other point, how far are we going to the right? How far are we moving horizontally from our vertex, Kendall?
Down 5 and over 1.
Okay, good. So when we go over 1, we're going down by 5. Now, normally, for our parent graph, we go over 1 and up 1, right? So in other words, our normal parent height times A has to equal our dilated height, right? So we come up with a little equation there then, right? We end up with 1 times A equals -5, right? Because we went down by 5. Well, that's easy to solve for A. A is just -5. And we got it. That make sense, everybody? See how we did that? Did we need the graph? Probably not. I mean, it's helpful to have, but we could have also just said, well, -1 minus 4 is -5, right? To see how far we moved. We didn't probably actually, we could have just subtracted the y coordinates, found the difference in the y coordinates to figure how far we went down. Okay, so there's our answer. Everybody agree with that? Okay, what about that one? Everybody try that one on your own real quick. So from the graph, you've got to be able to extract the values of A, H, and K by inspecting the graph. Okay, so Dulube, what are H and K?
Is H and K for negative 4? No, yeah, it's for negative 2.
4 and negative 2, good. Okay, now the tougher part is A. So what'd you get for A?
I wasn't quite sure, but I got negative 2 is A.
For A? Okay, okay, not negative 2. And what's probably a little bit tricky on this one is that the point goes to the left instead of the right. Let me know real quick, did that mess you up that the point was to the left instead of the right of the vertex? No? Okay. Okay, how are we going to get, everybody type in real quick if you're willing what you got for A. And somebody that got it right, I'm going to ask you how you got it. Okay, Maria, how'd you get 1/8? Because that's correct.
So at where the 0.00 is, if we have the same x value, the normal paragraph would be at negative 216.
Okay.
Because negative 4 squared is 16. But it only goes up 2.
Okay, good. That's a good way to think about it.
I did 16 divided by 2.
There you go. Good. That's a good way to do it, right? So look at our roadmap here, right? If we start from the vertex, we're going backwards, which is a little weird, right? I get that. That's a little weird. But we could go forwards or backwards because we have this axis of symmetry. So the roadmap to get from our vertex to this other point takes us over by negative 4. So we're going to move to the left from the vertex by negative 4. Now, normally, that's the same. And I could also have gone to the right by 4, incidentally, right? I could have also done this. Works either way. I could have gone to the right by positive 4 and used this point. That's okay. Normally, if I move 4 away from the vertex on our parent graph, how far would I have to go up? What do you think? How far would I have to go up, Adelaide, if I go over 4 on a regular parabola from the vertex? Questions for Adelaide. Did you hear me, Adelaide? The question was for you.
Can you say it again?
Yeah, sure. So on a normal parabola, if I go to the right by 4, how far up do I go? Right, and our parent graph is always just y equals x squared, right? Okay, f of x equals, so that's always what we're thinking in terms of, is just the graph of y equals x squared, right? And conveniently for us, we can see that the origin is on the vertex for our parent graph. It makes it easier to think about. If I go, let's look at some points here, right? The origin, or the vertex in this case, is at 0, 0. Right? If I go over to the right by 1, I go up by f of 1, which is 1 squared, right? If I go over by 2, I'm going up by f of 2, which is just 2 squared. I'm going up by 4. So you tell me, if I go over on the regular parent graph, if I go over by 4, how far up am I going? If I put 4 into my function, right, all I'm doing with my parent graph is squaring the input, right? 16, exactly, right? You see my point? So I'd be going over 4 and up 16 normally, right? But for this one, instead of going over 4 and up 16 or back 4 and up, it would work the same way, wouldn't it? Here I'm going either to the left 4 or to the right 4, and I'm only going up by 2. Okay? So my dilated height here is only 2. My parent height would normally be 16. And remember what A does. A is what we multiply by the parent height to get the dilated height. Okay? So 16 times A would have to equal my dilated height of 2. Well, A must be a pretty small fraction because I've squashed this thing quite a bit. It's been compressed quite a bit. If I divide both sides by 16, I get my answer. A is 2 over 16, which is 1 over 8. Okay? Give me a 1 to 5 on that. That's kind of a tricky concept. Okay? Okay. Let's try another one. I'm going to skip that. I want to do another one like this. Let me pull up the practice. Okay. Cancel. Oh, darn it. We're out of time. Okay. I'll tell you what. We'll go through your assignment. I'll put your assignment up. You can get started on it, but I'll go through a couple more problems next time. Okay. How are we feeling on this? Give me a 1 to 5 on this stuff. Okay. So we're not at 5 right now. I want us to be mostly at 5. So we're okay. So we're not quite there. So we need a little more time on this. All right, we'll do that. Get going on the assignment. You can jump into it, and we'll do a few more practice problems. All right. Have a great day, everybody. I'm here after school if you need me.